Welcome back to the series on linear algebra. If you've been following my videos, you might notice I'm back in MS Paint. I tried to use Microsoft OneNote for a bit because I thought it made the writing look nicer, but it made everything else worse, and so I know it might look a little sloppier, but hopefully this improves the quality of the videos overall. That's enough housekeeping. In this video, we're going to be talking about an algorithm that is used to solve systems of equations. This works for any system. It could be arbitrarily large, as long as that system is solvable. And so in this video, we're going to see how that algorithm called Gaussian Elimination works. And it's important because we don't really want to be solving these systems of equations. They're very tedious, take a long time. What we want to do is we want to program a computer to solve these problems for us. And computers actually solve systems of equations with Gaussian elimination. So we're going to see how that works. We're going to see what happens when the system doesn't have a solution and we try to solve it. And importantly, we're going to see about roughly how long it takes a computer to solve these types of problems. We're going to try to look at all those questions. All that's very important. So to start, we're going to look at the following 3x3 system. It says that the first variable, instead of using x, y, z, I'm going to start using this x1, x2, x3 notation, because when you get more than 3 variables, it's like, okay, I used x, y, z, what else do I use? So this is more common in linear algebra. And so we have these 3 equations here and these 3 unknowns. And the first thing I want to do is, because I don't want to be writing all of these pluses, all of these minuses, these equals, and these variables all the time, is that I'm going to try to convert this into that notation we saw earlier, where I'm going to write this as a matrix of coefficient times a vector of unknowns equals some vector on the right-hand side. And so the way that I'm going to write that is I'm going to use the coefficients here. So 1, 3, and -1, 2, 1, and -1. And then 4, 7, and 2. And then if I multiply this by the vector of variables here, x1, x2, and x3, then what's this going to give me? Well, this is going to give me a vector with 3 components, and each one is going to be the left-hand side of all these equations. x1 plus 3 times x2 minus x3 will be the first component of the result of this multiplication. So if I set this equal to another vector with 3 components, but this one being the right-hand side of this equation, that's our b vector here, this is going to tell us exactly the same thing as this whole system of equations. It's just, it's much more condensed. And speaking of being condensed, I want to be able to solve this system once again with much less writing. All right, so now what I want to do is I want to create a new matrix, which is going to have a different name, which is called an augmented matrix. I'm just going to show you what it is first and then explain it, because I think it's easier to understand with an example. So I'm taking my matrix of coefficients here, and then I'm going to draw a vertical line. This is just notation, just so I can have some visual separation. And then I'm going to write our right-hand side here. And now intuitively, the way that I want to understand this augmented matrix here is that on the left, I'm keeping track of the coefficients, and on the right, I'm keeping track of the right-hand side. And what I want to do is I want to do row operations on this new matrix. The 3 row operations are going to be multiplying any of these rows by a constant, adding these rows to each other, or we could do a combination of those. I could multiply this row by a constant and then add it to this row. Or I could swap the order of these rows. Now, if you watch the first video, those row operations correspond exactly to modifying the system. If I'm modifying the system and I multiply one of these statements by a constant on both sides, it's not going to change the set of variables that would satisfy that equation. If x1 plus 3x2 minus x3 equals 2, then if I multiply the left-hand side and the right-hand side by 4, or any constant, the same values of x1, x2, and x3 are going to satisfy that resultant statement. It's an equivalent statement. And so what I'm saying is that if I multiply the rows of this matrix, that's going to be the equivalent of doing that to this statement. And so this is just a way to save time writing. I don't want to write down all of these variables every single time. I don't want to write x1, x2, x3, and I don't want to write the pluses, the minuses, and the equals. And so instead, what I'm doing is I'm just keeping track of the coefficients, I'm keeping track of the right-hand side, and I'm going to do row operations on this matrix. It's exactly the same thing. So the way to interpret this is to say that this tells you the combination of the variables, and this tells you what it equals. And so 2 times x1 plus 1 times x2 minus x3 is going to equal 2. And so if I do a row operation, like adding the first row to the second, what that's telling us to do is to say, I'm adding this combination of variables to this combination of variables. But this combination of variables equals 2, and this one also equals 2. So if I add the right-hand side together and the coefficients on the variables, it's going to give me an equivalent statement. It's going to give me a statement that will be satisfied by the same values of x1, x2, and x3. And so in general, what I'm going to do is if I create an augmented matrix with the coefficient matrix on the left and the right-hand side on the right, I want to do row operations. And this is going to produce an equivalent statement, which I'm going to call A prime and B prime. And the hope is that this equivalent statement will be an equivalent system of equations, an equivalent system of statements that will be more useful. So like in the first video, what we saw is we could do operations to this system of equations, and our goal was to try to create a new system that was an equivalent system, but one of those statements would be something of the form a constant times just one of those variables equals something else. And then that would tell us the identity of that variable, and then we could work backwards to figure out the identity of the rest. And so that's what we want to try to do here. All right, so I think the best way to understand that is to just do an example again. So I'm going to solve this system of equations by doing row operations on this augmented matrix. And I'll show you the procedure. So the goal with Gaussian elimination is to take, for each column in the matrix, you try to eliminate all the entries below the first value. And then when you move forward, when you go to the next column, you also go to the next row. And so what we're going to do is we're going to try to turn these entries all into zeros, and then we'll move to the next column in the next row. We'll go to this entry here. We'll try to eliminate all the entries below it, turn those into zeros, and then we'll move to the next column, next row. There's no entries below this one, so we'll be done. And we'll talk about why that works in a second. But let's just do it. And so the first row is going to stay the same. And then I'm going to subtract 2 copies of row 1 from row 2. Or equivalently, I'm going to multiply row 1 by 2 and subtract it from row 2. I'm just doing 2 of those row operations in conjunction with one another. And so I'm going to get a 0 here. I'm subtracting 6 from 1. I get -5. I'm adding 2 to -1. I get 1. I'm subtracting 4 from 2. I get -2. Now I'm going to subtract 4 copies of row 1 from row 3. I'm going to get a 0 here. I'm subtracting 12 from 7. I also get a -5. And then I'm adding 4 to 2. I get a 6. And then I'm subtracting 8 from 21, which is 13. Okay. So that's a 1. Okay, just making sure that wasn't a 6. Okay, now I'm going to move to this entry here, and I want to knock out all of the values below it. And so I want to turn this -5 into a 0. The easy way to do that is to just subtract row 2 from row 1. Or, sorry, subtract row 2 from row 3. I'm going to copy this to save some writing. And eliminate these. Okay. When I subtract row 2 from row 3, I'm going to get a 0 here, of course. And I'm subtracting 1 from 6, I get a 5. And then I'm subtracting -2 from 13, so I get a 15. Okay. Now, I want to make the claim that this is a much better system. And this is our new, this is our new, I'm going to write this as our A prime x equals, well, sorry. This is the augmented matrix A prime B prime. So if I rewrite this as, A prime, if I solve A prime x here, that's going to be this vector of coefficients times our vector of unknowns, which is x1, x2, x3. And so that's going to equal a vector with 3 components. And the first one is going to be x1 plus 3, x2 minus x3. The next one is going to be -5, x2 plus x3. And the last one is going to be 5x3. And we're going to make the claim that this vector equals our right-hand side, our b vector, which has now changed. It's b prime. It's going to be 2, -2, and 15. And so this is exactly the same as a new 3x3 system, but this one is better because if we look at this last equation, this tells us 5x3 is equal to 15. And so that's exactly the same. I could multiply both sides by the same thing, but I don't even need to explain that. You know from Algebra 1 that this is the same as saying x3 is equal to 3. But now that I know that x3 is 3, I can go to the second equation, and I can plug that value in here, and this becomes negative 5x2 plus 3 equals negative 2, or equivalently, negative 5x2 equals negative 5, which tells us that x2 must equal 1. x2 must equal 1. And now we know x3 and we know x2, and so we can plug those values into the first equation here. We know x2, we know x3, so we get x1 plus 3 minus 3 equals 2. And that's exactly the same as x1 equals 2. And this gives us a solution to the system of equations. All right, so the key idea here with Gaussian elimination is that we take an n by n system, we reduce it to an n minus 1 by n minus 1 system, we reduce that to an n minus 2 by n minus 2 system, and we keep going until we get to a 1 by 1 system, which is really easy to solve. So in this case, we started with the 3 by 3 system, 3 equations with 3 unknowns, and then we eliminated this first column. And when we did that, this lower portion of the matrix right here, this is just a 2 by 2 system. It's because that first term is the coefficient on that variable in both of these equations is 0, so it just goes away. This is now just a 2 equations with 2 unknowns, and then we took that equation, we eliminated this one, and we reduced this to a 1 by 1 system, which is 1 equation with 1 unknown. 5x3 equals 15. Anybody could solve that. And then after we reduce this all the way down into this triangular system, which is going to have those properties, then what we could do is we could do what's called back substitution. Put that value into this equation, then put this value into this equation. And that's exactly what we did to solve this. That's how we got this answer. But we didn't have to write out all these equations either and, think about doing all those substitutions. One thing that we could have done is we could have just stayed with this matrix and continued to reduce it. So I'm going to show that now. If I just take this matrix, I say, okay, well, now let's keep going. And so I could take this last equation, I could divide both sides by 5. And so this becomes a 1, and this becomes a 3. Now that's the same thing as solving that 1 by 1 system, because now if I were to, multiply out all these equations, then what I would find is that the corresponding statement that went with this row of the matrix would tell us that x3 equals 3. But I can keep going. Now I could subtract row 3 from row 2. And when I do that, I have zeros in these, so I don't even need to worry about that. But this is going to become a 0. This will become a 0. And then I'm going to subtract row 3 from row 2. And so this negative 2 here is going to become a negative 5. It's going to become a negative 5. And so what just happened there was exactly the same thing as when I took this x3, substituted it into this equation, and then eliminated it from both sides to leave me with just negative 5x2 equals negative 5. But rather than, plugging things in, substituting them, and carrying out the multiplication, I just stuck with this matrix. I did the same thing. It's just a little bit less writing. Now I could continue to reduce this. I could take the second equation, divide both sides, or I could take the second row of the matrix, divide it by negative 5. This becomes a 1. And this also becomes a 1. This becomes a 1. This also becomes a 1. And now the only thing that's left is the first equation. And so I'm going to subtract row 3 from row 1, or add row 3 to row 1. That's going to become a 1. Or that's going to become a 0. This is going to become a 5. 0, 5. And then I'm going to subtract 3 times row 2 from row 1. And now this is going to become a 0. And I'm subtracting 3 from 5, so I get 2. 2. And so now what has happened here? Well, now I have a new system here, and this system is going to have the identity on the left-hand side, and the right-hand side, what's that going to be? What's going to be the vector we're looking for? It's going to be the solution to ax equals b. Because these are the values, like the corresponding system that goes with this. If I were to carry out this multiplication here, this would just be a vector x1, x2, and x3. It's just the identity times x1, x2, x3. It doesn't change. And so that's telling us that this equals 2, 1, 3. And so this is another way to solve the system. And you should note how staying with it's a good practice to think about how staying with the matrix and just eliminating things backwards, going and eliminating above the columns and then dividing to just create an identity matrix here, that is the same thing as what we did here in order to solve the system. It's the exact same thing. This is just less writing. Okay, hopefully all that made sense, and hopefully it will start to make even more sense as we continue to practice. But in general, the idea is just to do row operations on the augmented matrix of A and B. This is to solve the system of equations AX equals B. In order to solve that, we want to do row operations on the augmented matrix A and B in order to change it to U and B prime, where U is going to be some upper triangular matrix. And that's like this one right here. After we have that, we have two options. We can continue doing row operations to reduce that upper triangular matrix to the identity matrix. And as long as we're keeping track of the same things on the right-hand side, then we'll get the corresponding vector that we're looking for. We will have the solution to the system. Or equivalently, we could just use back substitution to find x. That's the difference between continuing to stay with the matrix to get to this form here, and then this tells us the solution, versus writing out the system and then using back substitution or to figure out what x3 is, then x2, then x1. They are the same thing, but in general, I think that staying with the matrix has less writing. Okay, let's look at another example. This one's going to be much more difficult, but it's actually important. It'll be relevant, and we'll see why. And so we're told that the sum of the first n natural numbers can be represented as a quadratic function of n. This is a very famous result in mathematics. You should definitely know this. If I want to sum up the first n natural numbers, 1 plus 2 plus 3 all the way up to n, actually I'll tell you the story. So the story is that Gauss, the same mathematician who's supposedly behind Gaussian elimination, he was, I think, 8 years old or he was a child, and the teacher was upset with the kids. They were being unruly, and so she was trying to punish them by making them do some tedious, mundane calculations. So she said, sum up the first numbers, 1 plus 2 plus 3, all the way up to 100. So all the kids are working on that, and Gauss gets it done in about 4 or 5 seconds. And the way that he does it is he notices a pattern. If you look at the first number and the last number, this is going to add together to give n plus 1. If you look at the next number and the second to last number, this is also going to add to n plus 1. And in general, if you pair these all up, you're always going to get n plus 1. And so the question is, how many pairs are there? Well, there's n numbers here, and so there's going to be n over 2 pairs. And so if I take n over 2 and I multiply it by the value, n plus 1, then this is going to give me the sum of the first n natural numbers, which I can write in summation notation like this. And you can check that yourself. For instance, if I want the sum of the first 4, this is going to give me 10. And if I do 4 times 5, that's 10, or sorry, that's 20 divided by 2, that's 10. And so it checks out. And you can check it yourself that this works. And so Gauss said, if you take 100 times 101, and then divide by 2, you get 50/50. And so he solved it in just a second. Now, suppose you know that the sum of the first n perfect squares is a cubic function. So this is a quadratic function because I could write this instead. I could write this as n squared over 2 plus n over 2, right? This is a quadratic function of n. That's what I mean by that. This is just a nicer way to write it, and it's more intuitive when you have the story that comes with it. And so suppose we know that the sum of the first n perfect squares, meaning this expression right here, the sum from I equals 1 to n of I squared, or 1 plus 2 squared, which is 4, plus 3 squared, which is 9, plus 16, etc. That's what we want to solve. We're supposing that we know that that's a cubic function. And this is actually true. It continues. For example, the sum of the first n perfect cubes is going to be a quartic function of n. And so we're asked to use Gaussian elimination to find a formula for the sum of the first n perfect squares. And the question is, how are we going to use Gaussian elimination to figure this out? Well, we can make up some notation. So we'll say that S sub n, this is going to denote the sum from I equals 1 to n of I squared. Okay, and we want to figure out a different formula for this. So we're supposing that we know that there's some set of coefficients a n cubed plus b n squared plus Cn plus D, that equals S sub n. And what we want to do is we want to figure out what these coefficients are. So they're actually going to be our unknown. And one way that we could do that is we see that there's 4 unknowns. And so we know we're going to need 4 equations. So let's just figure out 4 different values of S sub n. Obviously, S sub 1 is just going to be 1. S sub 2 is going to be 1 plus 4, which is 5. S sub 3 is going to be 5 plus the next one, which is 9. And so I'm going to get 14. And then S sub 4 is going to be 14 plus the next one, which is 16. So that's going to be 30. And so this gives us 4 values of this sum. Now I want to write this as a system of equations. Ax equals b. Now what's b going to be? That's the right-hand side of all of our equations. So that's going to be the value of the sum. It's going to be this right here. And so that's pretty easy. Now the question is, what is the variable here? Well, this x is the thing that we're solving for. And the thing that we wish we knew in this equation are these coefficients. And so x needs to be this vector right here. This needs to be a, b, c, and d. That's what x needs to be. And if that's what x is, then we could try to figure out what a is. We want a to be a matrix such that when we multiply it by this vector here, we will get this expression right here. And so what we need is we need n cubed, we need n squared, we need n, and we need a 1. So that when we multiply the row of this matrix by this, we get this expression right here. And so in order to actually solve the system, we're going to have to plug in n cubed, n squared, n, and 1. Obviously, the last column of this matrix is just going to be all 1s. But the rest, we're going to need to plug in n cubed, n squared, and n for different values of n. And so the 4 different values we're working with are 1, 2, 3, and 4. And so the first one's going to be easy because 1 cubed is 1, 1 squared is 1, and 1 is 1. And then the next one is 2. So 2 cubed is 8, 2 squared is 4, then we put 2, and we have a 1. And then we're working with 3, so we get 27, 9, and 3. Yeah, don't know why I paused on that one. And we have 64, we have 16, and we have 4. And so that's our matrix. This is giving us the values of n cubed in the first column, n squared in the second, n, and then 1. And so if we solve this matrix times this gives us b equals, that's going to be the right-hand side over here, which was 1, 5, 14, and 30. If we solve for this system for x, that's going to tell us the coefficient on this cubic function, and we'll figure out what our formula is. So that's how we're going to use, that's a setup, and that's how we're going to use Gaussian elimination to solve this problem. And so let's actually do it, solve the problem. And so I'm just going to copy this matrix here. Let's see, copy it right there. And then I'm going to set up that augmented matrix just as we did in the last example. And so I'm just going to write it because I think this is faster. 1, 5, 14, and 30. Okay, now let's use Gaussian elimination. So the first step is to eliminate this column. And so I'm going to subtract 8 copies. The first row is going to stay the same. 1, 1, 1, 1, 1. And then the second row is going to change. So I'm going to subtract 8 copies of the first row from the second. I'm going to get a 0 here. I'm going to get a negative 4 here. I'm going to get a negative 6 here. And a negative 7. And then 8 minus 5, or 5 minus 8 is going to be negative 3. Now I'm going to subtract 27 copies of the row 1 from row 3. This is going to become a 0. 9 minus 27 is going to be negative 18, right? And then I'm going to subtract 27. That's going to be negative 24. And then 1 minus 27 is negative 26. And then 14 minus 27, 27 minus that's 13, negative 13. Okay, negative 13. Now I need to subtract 64 copies of row 1 from row 3. Again, I'm going to get a 0, negative 48 here. Then I'm going to get negative 60 and negative 63 and 64, negative 34. Okay, that wasn't terrible. And I've now reduced this to a 3 by 3 system of equations. Okay. Now, one thing I'm going to do, just because it's going to make it easier for me, I'm pretty bad at arithmetic, is I'm going to take this whole row and I'm going to divide it by -4. So I'm going to try to remember these numbers, -4, -6, -7. And so I'm going to get 1, 3/2, and 7/4. And then I'm dividing by -4, so this is going to become 3/4. 3/4. Completely allowed to do that. And the reason I want to do that is because that's just going to make it easier for me. Now I'm going to try to eliminate these entries here. And so in order to do that, I need to multiply. Let's just copy this. It's going to be easier. I'm going to multiply row 2 by 18 and add it to row 3. Okay, so what am I going to get when I do that? I'm just going to delete this and then fill it out as I go. When I multiply row 2 by 18, I'm going to get 18 plus -18. That's going to be 0. And then when I multiply this by 18, it's just 3 times 9, which is 27 plus -24 is 3. And then this is going to be 18 times 7/4 is going to be 9 times 7/2. 9 times 7 is 63. So this is going to be 63/2. 63/2 minus 26, which is 52/2. And so this is going to be 11/2. 11/2. Okay. And then finally, 3/4 times 18 is going to be 27/2. 27/2 minus 13, which is 26/2, is going to be 1/2 in this entry. Okay. Got another one here. I need to add 48 copies of this row to the third row. This is going to become a 0. 48 times 3/2 is just going to be 24 times 3, which is 12 times 6, which is 72. 72 minus 60 is 12. Okay. 48 times 7/4 is 12 times 7, which is 84. Then I add 84 to 63 here. That's 84 minus 63 equals a 1 and a 2, so I get a 21. Okay, and then 48. 48 times 3/4 is going to be 12 times 3, which is 36 minus 34, and I get a 2 here. All right, that produced, somewhat nicely. Not as bad anymore. And so we're getting close here. I'm going to just continue with the procedure. And so now I'm going to subtract 4 copies of row 3 from row 4. Let's just delete this all at once now. That'll be easier. And so I'm going to do 12 minus 12. It's going to be 0. Then 21 minus 4 times 11/2. That's 22. So this is a -1. And then 2 minus 2, that's going to give me a 0 here. And so now I have 2 options here. I could do back substitution, or I could just stick with this matrix and continue reducing it. And I would rather just stick with this matrix and continue reducing it, because I believe it's less writing. So I'm going to take this last row here, divide it by -1 to get a 1 here. And I just want to continue reducing this to identity. Now, the first thing to do to start here is to eliminate these entries using row 4 here. Now, one thing I'm going to notice is that what I would do to do that is I would multiply row 4 by -11/2 and then add it to row 3. But what I'm noticing is that because there's a 0 here and there's zeros over here, none of these columns are going to change. I can multiply by whatever I want and add them to the other rows, and none of them are going to change. And so I'm free to eliminate all of these without even thinking about it, because it's not going to affect any of the other entries. So that's going to save us a lot of time here. All that's just going to become 0, and it won't change anything else. And now in the second row, I just divide it by 3, and I get a 1 and a 1/6. Get a 1 and a 1/6. And now I want to subtract 3/2 copies of row 3 from row 1. And so this is going to go away. It's going to be 0. And then what's 3/2 times 1/6? That's going to be 3/12, which is 1/4. So I'm subtracting 1/4 from 3/4. That's going to give us 2/4, which is just 1/2. Which is just 1/2. And so now I need to subtract one copy of row 2 from row 1 to get rid of that, and one copy of row 3 from row 1 to get rid of that. And so when I do that, these are going to turn into zeros, and I'll finally have the identity here. And then the value here is going to be 1 minus 1/2 minus 1/6, which this is going to be 6 over 6. This is going to be 3 over 6. So this is going to be, the final value here will be 2 over 6, which is 1/3. Which is 1/3. Okay, 1/3 here. This is taking, there we go, 1/3. And we're done. We've reduced this to the identity, which means that if I look at this equivalent system of equations here, this is going to tell me that A is equal to 1/3, B is equal to 1/2, C is equal to 1/6, and D is equal to 0. Or equivalently, that the sum, the first n perfect squares, I can write it this way, I is equal to 1 to n I squared. This is going to equal 1/3 n cubed plus 1/2 n squared plus 1/6 n. Now, obviously this works for n equals 1. That value is going to be 1, and then you just add these fractions together, you get 1. But you could verify it for other values of n. And then this will let you compute the sum of the first, 100 perfect squares pretty quickly. You just type, this expression into a calculator. Now, one thing to note is that we can reduce this. So I could factor out an n over 6 here. And so this is equal to n over 6 times, and then what am I going to get? Here I'll get 2n cubed plus, and then factor out a 1 over 6 here, I get 3n squared, I think. And then a 1. This should be an n, and this should be n squared. And now I can actually factor this quadratic as well, because I could split the middle here. I get 2n squared plus 2n plus n plus 1. And this is the same as 2n times n plus 1. Plus 1 times n plus 1. And so I can rewrite this as 2n plus 1 times n plus 1. And so if I factor everything, I can rewrite this whole equation as 2n plus 1 times n plus 1 times n over 6. And so this is the formula you usually see this as. Hopefully that example made sense and wasn't too difficult. Now, I want to go over some terminology. I don't know why in linear algebra we have some of these super specific words, but you will probably see these words when you're going over a linear algebra textbook or reading about linear algebra, so it's important that you know what they are. When we're doing this process of elimination, the diagonal entries that we use to eliminate the entries below them, they're called pivots. And so I'm not exactly sure why they're called pivots. I couldn't find anything online about it. But I guess the idea is that when you're going through the process of elimination, one of those entries stays fixed, and you use that to eliminate the ones beneath it, so you're kind of pivoting around it. I don't know. That doesn't make as much sense, but these other ones make more sense. We have row echelon form, sometimes abbreviated REF. A matrix is in row echelon form when rows of all zeros are at the bottom, and the pivot of each row, that leading entry, is to the right of the pivot of the row before it. This terminology comes from military terminology for echelon form. So I have some pictures here, and when I do this example on the bottom and we find the row echelon form and the reduced row echelon form of the matrix down here, we'll see the resemblance between these things. Now, when we do forward elimination, Gaussian elimination, we take this augmented matrix with A and B, and in order to solve it, we do row operations on this augmented matrix to produce a new augmented matrix that will have an equivalent solution space, where the matrix on the left is this row echelon form matrix. And so that's that triangular matrix when we're dealing with the square matrix, for example. And then the right-hand side is different because it has to change when the left-hand side changes. But that's the objective, is to change A into row echelon form so that we can solve for the solution. And then there's also reduced row echelon form, where it's in row echelon form, but the pivot in each row is a 1. That's that diagonal entry we use to eliminate everything. And in each column containing a pivot, the pivot is the only non-zero entry. So we're going to look at that with this example. Now, I would say, I almost want to say that a triangular matrix is in row echelon form, but it's not necessarily, and we'll see why. So I want to talk about, they're similar, but they're not exactly the same. And so we'll talk about that in a second. I think right now, just to sort of understand this terminology, I want to find the row echelon form of this matrix. And so, as I said, up here, the way that when we do elimination, we're reducing the matrix to its row echelon form. So we'll just do elimination on this matrix, even though it doesn't correspond to a system of equations. So I'm going to leave the first row untouched, and then I'm going to subtract 3 copies of row 1 from row 2, and this is going to become a 0, and then I'm going to get -2 here, I'm going to get -1 here, and I'm going to get a 0 here. Now I'm going to knock out this entry on the bottom. And so I'm just going to subtract 1 copy of row 1 from row 2, and I get a row of all zeros. Now, this matrix is in row echelon form. This is REF of, A. Let's call this matrix A. This is because the pivot in each row, that leading diagonal entry that we would use to knock out any remaining entries were there any non-zero entries beneath it, this pivot is to the right of this pivot. And so it makes this, echelon pattern, kind of like what we see here with the troops and the ships. So that's why it's called that. But if we want to turn this into a reduced row echelon form matrix, then we need 2 things. We need the leading pivot in each row to be a 1, and then we also need the pivot to be the only non-zero entry in that column. And so we need to use this to eliminate the entry above it. And so I'll just divide row 2 by -2. And so I'll get a 1 here. I'll get a 1/2 here. And I'll get a 0 here. And then I want to subtract 2 copies of row 2 from row 1. There's a 0 in this entry, so this entry isn't going to change. And then when I subtract 2 copies of 1 from 2, I'm going to get 0. When I subtract 2 copies of 1/2 from 1, I'm going to get 0. And when I subtract 2 copies of 0 from 1, I'm going to get 1. And now this is in reduced row echelon form, because the pivot in each row, that leading entry on the diagonal, that's a 1 in every one of these cases, and that 1 is the only non-zero entry in both of those rows. Now, I do want to explain the difference between a triangular matrix and row echelon form, because these 2 matrices are already examples of matrices that are in row echelon or reduced row echelon, but are not triangular matrices, because a triangular matrix has to be a square matrix with zeros below the main diagonal. So these are rectangular matrices, so they could be in row echelon form, but they can't be triangular. But you can also have a triangular matrix that's not in row echelon form. For example, if I have like a 3x3 matrix and there's entries in the first row, and then let's say in this row it's like a 1, and then in this row there's a 4 here. This is a triangular matrix because it's zeros all below the main diagonal. However, it's not in row echelon form because the pivot in this row is not to the right of this row. And so to make this into row echelon form, I would need to subtract 4 copies of this row from this one to knock out this pivot and have a row of all zeros at the bottom. Now, I do want to make a point here. If we have a square matrix and we're trying to solve a system of equations, meaning we are going to take our coefficient matrix, it's a square matrix, we've got n equations and n unknowns, and we're going to make an augmented matrix with our right-hand side, and we want to find the solutions to ax equals b, or the solution to ax equals b. So we construct this augmented matrix, we do row operations to reduce the left matrix, or to reduce this augmented matrix to row echelon form, but that's going to result in some type of triangular matrix on the left and a different right-hand side. Now, I just want to use a 2x2 example here to illustrate this. If this reduced form winds up like this, where we have some value here, and then a 0 and a 0, and this is the first component of b prime, and this is the second component. If this is the situation we wind up in, where we only have one pivot in this 2x2 resultant coefficient matrix, then this solution, the solution to this system is either going to be infinitely many or none, because there's only two possibilities here. On the bottom here, remember, this is the combination of variables, so this is saying taking none of those variables. Either that's going to equal 0, and then there will be infinitely many solutions here, because it will just be the combination of variables that satisfies u11 times x1 plus u12 times x2 equals b prime 1, which that's just a line. And so there's infinitely many solutions to that. Or this b prime 2 is going to be some value other than 0. And then this statement here tells us that 0 equals b prime 2, which will be a contradiction if b prime 2 is not 0. And so when we get to this stage, we know that there's either infinitely many or no solution to our system of equations. But if instead we get to this point where we have an entry here, u21, and this entry is not equal to 0, then I can tell you for sure that this system is going to be solvable, because I can tell you right off the bat what the solutions are. It's just the second variable is going to be b prime 2 over u21. That's going to be our second variable. And then our first variable will just be this value times u12, and you subtract that for b prime 2. So that's going to be x1 is going to equal b prime 1 minus u12 b prime 2 over u21. So this is our solution. And because u21 is not equal to 0, this is well defined. And I guess this is easiest to see in the 2x2 case, which is why I chose to do that. But the point is, if I do row operations and I get my matrix to reduce or to row echelon form, and I find that I still have a full set of pivots. Here, this is a 2x2 matrix with 2 pivots. I can guarantee you that that system of equations is going to have a well-defined solution. Now, on the other hand, if I have less pivots, then, like, if I don't have a full set of pivots, if there's rows of all zeros, then I can tell you that there's for sure either going to be infinitely many or no solution to my system of equations. All right, so with that in mind, I want to look at a more illuminating example. I want to find the row echelon form of this matrix A, but this matrix, the entries in here can be literally anything. So this is just an arbitrary 2x2 matrix with A not equal to 0. And so in order to do this, I want to use the first row to eliminate the second row. So I'm going to multiply this first row by something such that the first entry will become negative c. So the obvious thing to multiply by here is negative c over a. I'm going to multiply this, it'll get negative c, and I add here, I get 0. So I'm going to multiply that first row by negative c over a and add it to the second row. I'm going to get a 0 here, and then here I'm going to get d minus bc over a. But I can rewrite this by finding a common denominator. D is just dA over A. And so this is going to be dA minus BC over A. dA minus BC over A. Now, I'll tell you, if you hand me any 2x2 matrix, doesn't matter what the entries are, the reduced, or the row echelon form of that matrix is going to be this right here. Always. Now, there's an issue here, right? Which is the way, if this is a matrix of coefficients and I'm trying to solve a system of equations, then I'll have a full set of pivots if and only if this value in the numerator here is not equal to 0. If this value is equal to 0, then I won't have a full set of pivots, and as we just showed, then what's going to happen is I won't have a well-defined solution. It's either going to be infinitely many, and it'll be some type of line, or there will be no solution to our system, depending on what our right-hand side looks like. So if I just have that dA minus BC is not equal to 0 here, then what's going to happen is the system of equations will be solvable and we'll have a full set of pivots. Or I guess, to be more precise, the row echelon form of our matrix will have a full set of pivots, and because of that, any system of equations with this coefficient matrix will have a well-defined single solution for any right-hand side. Now, let's just look at some cases where this quantity is equal to 0. Okay, and one thing I want to point out is that if dA minus BC is equal to 0, then if I were to solve this equation for D, I'm going to get BC over A. And that tells us that the second row of our matrix is going to be C, and then D is BC over A. BC over A. But this is the same thing. This is the same thing as C over A times A B. Because when I multiply C over A by A, I'm going to get C. When I multiply by B, I'm going to get BC over A, which is just D. And so that tells us that the second row of A is just going to be some value times this, which is the first row of A. And so that's a fact that we can determine from this, which means that there are several ways to tell if our 2x2 coefficient matrix is going to correspond to a system of equations that has a well-defined solution, or one that either is going to have infinitely many or no solutions. This is several ways for us to tell whether that system of equations is going to be solvable. And in the 2x2 case, if we're looking at a matrix and our second row is some multiple of the first row, I'll tell you that the system of equations that corresponds with that coefficient matrix is not going to have a well-defined single solution. But if it doesn't, or if this quantity here is not equal to 0, or if the row echelon form of that matrix has a full set of pivots, or equivalently, if the reduced row echelon form of that matrix is the identity matrix, which you can see if this quantity is not equal to 0, then I could take this whole bottom row here and just multiply by A over dA minus BC, which I can do. A over dA minus BC. I can multiply this because this quantity here is not equal to 0. So this is just some number. And when I do this, I'm going to get a 1 here. And then I can multiply by negative B and add it to the first row to knock out this entry. And I can divide the first row by A. So equivalently, if this quantity is not equal to 0, then the reduced row echelon form of our matrix is going to equal the identity in this case. And so all of these are different ways to tell me if the system of equations that corresponds with this coefficient matrix is going to have a solution. Reduced row echelon form is the identity. Row echelon form has a full set of pivots. dA minus BC is not equal to 0. All of these tell us the same thing, that our system of equations that corresponds with this coefficient matrix is going to have a well-defined solution. If that felt a little rushed, don't worry. Linear algebra is full of stuff like this where you want to know something about a matrix and there's 8 different ways to say it. So don't worry, we're definitely going to come back to these ideas probably in the beginning of next video for review. But in this video, I do want to make sure I touch on the complexity of Gaussian elimination. How difficult is it to find the row echelon form of a matrix? How hard is that going to be? And if you're like me, after that example with the sum of the first in perfect squares, that's doing Gaussian elimination on a 4x4 matrix, a 4x4 system of equations. And after that example, I never want to do a Gaussian elimination problem ever again. I want to get a computer to do it for me. And so we want to understand how this problem is going to grow as the inputs to our computer program grow in size, as our coefficient matrix grows, as we get more equations and things like that. And so the easiest way to understand that is to try to figure out how many operations is the computer going to have to do. All right, so if I have a matrix, and it could be just an arbitrarily large matrix, say it's n by n, but it's square. And we want to say how many operations is it going to take a computer to take this matrix and compute its row echelon form, or this triangular equivalent. Well, if I just draw out the matrix A so that we have some visual to go with this, there's A11, A12, A22, A21. This is going to go all the way down to AN1, ANN, and A1N. 1N. This is what our matrix looks like. Okay, so let's try to figure out what the computer needs to do. Well, we're going to start with the first entry, and we're going to pivot around this, and we're going to use this to eliminate the entries beneath it. And so let's just try to figure out how many operations this is going to take the computer to eliminate this entry? Well, we need to do a row operation. We need to multiply row 1 by a constant, and we need to add it to row 2. And so what does that mean? Well, that means that we need to take the ith entry in row 2, and we need to say that this entry is going to equal the entry in row 2, and then we're going to add to that some constant. And what's that constant going to be? It's going to be negative a21 divided by a11. And we're going to multiply this by the entry in row 1. So this is going to be 1i. Okay, so this is exactly what we need to do when we're doing our row operation. We are doing this. We're taking the entry in the second row, this entry, and we're adding to it a constant multiplied by the entry in the first row. And what is that constant? It's going to be negative a21 over a11, because when I is equal to 1, we're going to get a21 is equal to a21 plus negative a21 over a11 times a11 here, and then this is going to cancel, and then this is going to become 0. So that's why that's the constant that we need. But we're going to do this for every I. So 1 to n. And so here what we're doing is we're doing several things. First of all, we're doing assignment. I'm taking the value in the matrix and I'm changing it to something else. I'm doing addition, I'm doing division, I'm doing multiplication, and that's it. And so I'm doing several things, but all of these things, addition, multiplication, division, assignment, a computer can do all of those things relatively instantaneously. So I'm just going to count this as one operation for the sake of simplicity. But I need to do this one series of arithmetic operations. I need to do that for every entry in the row. And there's n entries in the row. So I'm going to say that for, in order to do one row operation, I'm going to say that this costs n operations. And it's n of these. And so in order to eliminate this entry, it's going to take n operations. And then the question is, how many entries do I need to eliminate? Well, I need to do every single thing beneath this entry right here. And so that's n minus 1 row operations that I need to do. So the total number of operations to eliminate the first column, or the entries below the diagonal in the first column, costs n times n minus 1 operations. That's every row operation is going to cost n minus 1 operations, and we need to do n minus 1 row operations. Okay, now what about the next column? Now we move to this entry, and we want to eliminate all the ones beneath it. And so I think the easiest way to see this is that if I just, once I move to this second pivot point here, once I move to this one, I no longer need to worry about this column at all because it's all going to be zeros. And so I think the best way to see this is that now I'm essentially just dealing with an n minus 1 by n minus 1 matrix. I'm dealing with this submatrix here. And when I'm asking, well, how many operations is it going to take to eliminate the entries below the pivot? In this case, well, it's the same exact question that we just answered, but for a smaller matrix. And so the answer is going to be n minus 1 by n minus 2. And if that doesn't make sense, it's just consider that every row of this matrix is going to have n minus 1 entries. So for every row operation, we need to do n minus 1 operations. And how many row operations do we do? Well, there's n minus 2 entries beneath this pivot point, and so there's n minus 2 operations. So this is the total number of operations it's going to take to eliminate the second column. And so I hope that that helps you see the recursive structure, because the next case is we're going to look at the next pivot. We're looking at a smaller matrix. And it's exactly how we described earlier in the video of taking an n by n matrix, reducing it to an n-1 by n-1 matrix, etc. But I hope you see the pattern, and the total number of operations is going to look like this. It's going to be n times n-1 plus n-1 times n-2. That's going to the second column, eliminating all the entries below the pivot, and then n-2 times n-3. That's how many operations it takes to eliminate all the entries below the third pivot, and then we'll go all the way down to 2 times 1. And so we can write this more succinctly with summation notation. This is going to be the sum from I equals 1 to n of I times I minus 1. Now, this is the exact same thing. It's just instead of going from the big term to the small term, the first entry in this sum is going to be, 0, and then the second entry is going to be 2 times 1. And so it's going to go from that, and the last entry is going to be n times n minus 1. N times n minus 1. And so this sum is exactly the same thing, but I want to work with the sum because we can rewrite this as I equals 1 to n of I squared minus I. And this is equal to the sum from I equals 1 to n I squared minus the sum I equals 1 to n of I. All right, hopefully now you might notice that there's a reason why I picked such a complicated example for my 4x4 system of equations and using Gaussian elimination, is because this term right here, that's the sum of the first n perfect squares. And this term is the sum of the first n integers. So we just found a way to express these in terms of n. And so this is going to equal 2n plus 1 times n plus 1 times n over 6 minus n times n plus 1 over 2. Now, I won't bore you with the algebraic details, but if you remember, we could rewrite this as 1/3 n cubed plus 1/2 n squared plus 1/6 n. And this is obviously minus n squared over 2 minus n over 2. And then these terms cancel. Then 1/6 n minus n over 2 is going to be negative 1/3 n. So this winds up reducing to this number of operations. That's what it costs to take our coefficient matrix and make it into a upper triangular matrix through forward elimination. But if you remember, that's just part of the story. And if I want to solve a system of equations, then I need to take that matrix in row echelon form, and I have two options. I could do the back substitution, or I can just continue reducing until I get to the identity matrix, provided that is the reducer echelon form of that matrix and the matrix is solvable, or equivalently that the matrix is solvable. But those two things are going to take the same amount of operations conceptually. So I'm just going to consider how many operations does it take to take the upper triangular version of a matrix and reduce it to the identity. So that's what we're going to answer next. This is going to go much faster. So I have my upper triangular matrix here with zeros below the diagonal. And I want to say how many operations is it going to cost to reduce this fully to reduced row echelon form, or equivalently to solve my system of equations. And so the first thing I need to do is I need to divide this last row by u and n to get a 1 in the pivot point here. That's going to take 1 operation. And then the next thing I need to do is I need to eliminate the entry above it, which will involve multiplying the bottom entry by negative u n minus 1 n, and then adding it to the next one. Multiplying by constant and adding to the next one just to knock out the entries above it. And because the computer is going to do all those things relatively instantly, I'm just going to count that as 1 operation. So it's 1 operation to divide this entry, 1 to eliminate the one above it, all the way up to the top. And so in total, it's going to cost n operations. And then how many operations is it going to cost to go to the next entry and then eliminate all the ones above that and turn this pivot point into a 1? It's going to take one operation to divide that row, and then we don't need to worry about the entries in this column. And also, all the entries to the left here are zeros, so we don't need to worry about the entries in any other part of the matrix. We only need to worry about the entries in this column, and so that's going to cost, again, this is going to just cost n-1 operations. And so hopefully you see the pattern. We're doing this for every single column, and so when we're going backwards, it's going to be n operations plus n-1 plus n-2 plus, and then we're going to end on a 1, which is just to divide this entry by u11 to get a 1 in the pivot. Now again, this is just the sum of the first n integers. So this goes I equals 1 to n of I, and we saw that this is just n times n plus 1 over 2. And so if I, were to add this and say, oh, what's the cost of taking a matrix and reducing it down to reduced row echelon form? Well, the answer is going to be this cost plus this, or an easier way to see it, it's just going to be the sum of the first n perfect squares, because here I subtracted this value, and then the cost of going backwards is going to add this value. We're just going to add it back. And so the total number of operations to reduce this matrix down to its reduced row echelon form is total number of operations to find the reduced row echelon form of A is going to be the sum of the first n perfect squares. And so that's going to equal 1/3 n cubed plus 1/2 n squared plus 1/6. Yeah. Now we're very close to being finished here, but we are forgetting about one piece. So when we want to solve the system of equations, we stick our coefficient matrix on the left of an augmented matrix with our right-hand side on the right. And then we do a series of row operations to either transform to upper triangular and use back substitution, or the easier way to see it is to just transform this matrix on the left into the identity, which it will transform into the identity if there's a well-defined solution, as we showed in the 2x2 case, but this is always true for an n-by-n matrix. We use row operations to transform this into the identity, and what we'll get on the right-hand side here is our solution vector. And so what we have found is the number of operations. This value right here tells us how many operations it's going to take a computer to go from this matrix to this one. But we haven't counted the operations on the right. For every operation that we do on the left, we also need to do it to the right-hand side. And so let's see how that's going to look. If I draw our augmented matrix here, we have our coefficient here, matrix here, but I'm not going to worry about that right now. Right now, I'm only interested in the entries on the right-hand side, and so that's going to look something like this. There's going to be n components here. Now, when we do forward elimination, we start with the first pivot, and we eliminate downwards. And so that's going to be n-1 operations. I need to multiply this by a constant, add it to the next row. Multiply by a constant, add to the next row, add to the third row, and do that for n-1 rows. And so there's going to be some series of arithmetic operations for each one of these pivots that for each one of these entries below the pivot that we eliminate. We're going to do a series of arithmetic operations that I'm going to count as just one operation. And so it's going to be one operation for every one of these entries that we eliminate, which is n-1. And so I'm going to say to clear out this first column is going to cost us n-1 operations on the right-hand side. And analogously, when we move to the second pivot and we knock out the entries below that, for every one of these pivots that we eliminate on the left in this coefficient matrix, we need to do some series of arithmetic operations on the right. And so there's n-2 of those, and so I'm going to say it's going to cost us n-2 operations for the next pivot. And we need to do this for every one of the pivots. And so finally, when we get to the second to last pivot, we're going to do one operation. And so this is going to be the operation count on the right-hand side in the forward direction. That's what this is. And what this is the sum of the first n-1 integers. And if we just use our formula for the sum of the first integers, which is n times n plus 1 over 2, but we plug in n minus 1, we'll get n minus 1 times n over 2. So that's our operation count in the forward direction. Now, what about in the backward direction? In the backward direction on the right-hand side. Well, the first thing that we do is we need to change this last pivot to a 1. And so that's going to cost one operation to divide. And then we don't need to worry about the entries on this side because they're all going to be zeros. Never mind, we're only working on the right-hand side anyway. So I need to divide this by the pivot, and then I need to knock out the entries above this. Now, when I do this, I actually do need to worry about the right-hand side, because there's entries here. And so I'm going to need to multiply this by some value and add it to every single entry above it, just as I do here to eliminate these entries. And so there's going to be one operation to divide by the pivot, and then n minus 1 to multiply that last entry by a value and add it to the rows above it. And so that's n total operations. And then when we move to the next pivot, we divide by the pivot on the right-hand side, and then we're going to multiply by some constant and add to every row above it. So it's going to be n minus 1 operations. We're going to proceed in this fashion all the way until we get to the last pivot right here, and then the only thing I need to do on the right-hand side is just divide by the pivot to get a 1 in that pivot position. And so this is actually just the sum of the first n integers. And so we have a closed form expression for this in terms of n. This is n times n plus 1 over 2. So in total, on the right-hand side, the total operations on the right-hand side is going to be this expression plus this one, which is n times n plus 1 over 2 plus n times n minus 1 over 2. And you can see that this is, n squared over 2 plus n over 2, and then this is n squared over 2 minus n over 2. So the n over 2's will cancel, and we'll just be left with n squared. So the total number of operations that we expect a computer to have to do in order to solve an arbitrary n by n system of equations is going to be this number of operations on the left, and we add to this n squared for all the operations on the right-hand side. And so this is going to be, the total will be, let's just copy this here, because I don't want to get it wrong when I remember it. But I'm going to add to this n squared, and I'll get 1/3 n cubed plus 3/2 n squared plus 1/6 n. This is the total operations to solve an n by n system. That's what this is. All right, so to end this video off, I want to show that what we just figured out is actually useful. So I'm in RStudio. This is the IDE for the programming language R, which is pretty easy. Now, you don't need to know how to code. I'm going to explain what all this is. This is a function right here to compute how long it takes R, the programming language, to solve a system of equations that's n by n. And so what it's going to do is it's going to generate a random n by n matrix and a random vector in R to the n. And then it's going to solve that system of equations, and it's going to record how long it takes. And it's going to do that for the amount of repetitions you tell it to do, which in here I've defaulted to 3, and then it's going to record the average of those. And so let's use this function to try to figure out how long it takes R to solve a 1,000 by 1,000 system of equations. This is going to go pretty fast, and then if you look over here, it tells us that it took R on average 0.16 seconds to solve a 1,000 by 1,000 system of equations. And now let's see how long it takes R to solve a 5,000 by 5,000 system of equations. Now, this is going to take a little bit, so while it's running, I'm going to write a few more functions. First one is going to be the operation count function. So this is going to take n as an argument, and what it's going to return is it's going to return the operation count we're estimating based off of that equation we just derived. So this would be 3/2 n squared plus n over 6. And so this is going to tell us the number of operations we're predicting the computer will have to do in order to solve the system of equations. And now what I want to do is I want to write a function that will predict the amount of time that it will take the computer to solve a system of equations. Now, I don't really know how long it's going to take R to solve a system of equations, but I can figure out how long it will take for R to solve 1,000 by 1,000 system of equations, and then I can try to estimate how long it's going to take to solve larger systems based off of that. So I'm going to use our operation count function, and I'm going to compute the ratio between the operation count we estimate for some value and divide that by the operation count we estimate for an observed value. And then I'm going to multiply that ratio by the time it took for that observable time. And so maybe that doesn't make sense, but let's just write it out. Do the operation count for some constant multiplied by 1,000 divided by the operation count for 1,000. And then I'm going to multiply this ratio by the actual time it took, the actual time we observed for the computer to solve 1,000 by 1,000 system of equations. And so what this function is going to do is it's going to say, okay, let's take the operation count, which the computer can solve instantly. This is just computing this function. It's going to take it no time at all to figure this out. For a system of equations that's, a times 1,000 by a times 1,000, and we'll take that ratio divided by the operation count of 1,000. We're taking that ratio and we're multiplying by the time it took the system to solve 1,000 by 1,000 system of equations. And so this is going to give us an estimate for the time it will take to solve an a times 1,000 by a times 1,000 system of equations. And I can't actually run any of this code until this one finishes, which is going to take a long time because it takes the computer a long time to solve a 10,000 by 10,000 system. So I'm just going to cut the video and come back. All right, I'm back. It's been about 7 minutes and it finished running. And it said for a 10,000 by 10,000 system of equations, it took R about 137 seconds. And now we can store these functions and we can show that we can use this operation count to try to predict these values. And so let's try to predict, I'm doing this at the bottom here, the amount of time it will take to solve a 5,000 by 5,000 system of equations. Here I'm going to pass in 5 because that's the value that I'm multiplying 1,000 by here. And this is what I'm going to get. I'm going to get 19 seconds. So the actual time it took was 17.9 seconds. And I can tell you that the value we predict is always going to be greater than the value that we observe because these matrix operations are so important for computers that so much time, so much research, so much dedication has been spent to optimizing these protocols as much as humanly possible. So every programming language that you use, Python, R, they have all of these optimizations built in to make matrix multiplication as fast as possible, make solving these systems as fast as possible. So the result of that optimization protocol is we get 17.9 seconds to solve this on average instead of 19.5, which is what we predicted. But what we predict is still pretty accurate. So let's see what we would predict for a 10,000 by 10,000 matrix. So I'm going to pass predicted time. This time I'm going to pass in 10 because that would be the value I need to multiply 1,000 by. And we would predict that it would take the computer about 156 seconds to solve a 10,000 by 10,000 system. And the actual value we observe, as we would expect, is just a little bit under that. It took 137 seconds for R on average to solve these. Now, the reason I'm showing you this is because, yes, I will expect it to be just a little bit less than what we're going to predict, but this predicted time based off of this operation count function is going to give us a good idea of how long it will take for us to solve these systems. And obviously the amount of time it's going to take is going to depend on what computer you're using. So if you have a really powerful computer, maybe this initial value will be much smaller. And that's why we're basing our prediction for my system based off of the observed time on my computer. But the reason I'm showing you this, right, is because if I want to see how long is it going to take for R to solve like 100,000 by 100,000 system of equations, I get this value right here, which let's just go ahead and convert this to hours. I have to divide by 60, and then divide by 60 again, which is the same as dividing by 60 squared. And so it would take this many hours. 43 hours. That's how long it would take that's what we would predict. So it'd probably be a little bit less than this. Maybe it might be 40 hours or 30 hours, but I'm not going to try to run it to observe that because that's already outrageous. And so in this case, it's instant for me to predict how long it's going to take to solve that system of equations on this computer, versus actually trying to run it and actually trying to observe how long it takes would be annoying. You'd have to run your computer, you would have to leave your computer running for like 40 hours. And so that's why what we're doing here is actually useful, because ultimately we want to use computers to solve these problems, and we want to understand how these problems will grow as, or how the amount of time it will take the computer to solve these problems will grow as the scope of the inputs to these problems grows. So thank you so much for watching. In the next video, we're going to talk about how Gaussian elimination relates to matrix multiplication. We're talking about LU factorization and inverse matrices.